This question was asked in the GATE Physics paper 2020. This is a MCQ type question having 1 mark. The topic of the question is electromagnetic theory. The question is a medium with relative permittivity or dielectric constant epsilon r greater than 1, relative permeability mu r equals to 1 and conductivity sigma greater than 0 is semi-transparent to an electromagnetic wave when option A, conduction current is very greater than displacement current. Option B, conduction current is very less than displacement current. Option C, conduction current equals to displacement current. And the last option, option D, both conduction current and displacement current are 0. So let us see how to solve this problem. For a linear, homogeneous and isotropic conducting media, the Maxwell's equation can be written as curl of H vector equals to JC vector plus JD vector. So this is also known as modified Ampere's law. In this equation, the H vector is the magnetic field intensity vector, JC vector is the conduction current density, and JD vector is the displacement current density. Now, the conduction current density JC vector is given by sigma times E vector. Here sigma is the conductivity of the media and E vector is the electric field vector. And the displacement current density JD vector is given by del D del T. Here D vector is the displacement vector. Now this is also given by epsilon times del E del T. Here epsilon is the permittivity of that medium. Now if we consider a plane wave or monochromatic wave solution for the electric field, then it can be written as E vector as a function of r vector comma time, that is t, equals to E naught vector times e to the power I k dot r minus omega t. Here E naught is the amplitude of the electric field and k vector is the wave vector for that electric field. Now the conduction current density Jc is given by sigma times E vector. Now we'll put this E vector expression in this equation. So we'll get Jc vector equals to sigma times E naught vector times exponential of I times k dot r minus omega t. And the displacement current density vector will be given by epsilon times del E del t. So we'll put the expression for E vector in this partial derivatives and we'll get epsilon times minus I omega times E naught vector times exponential of I k dot r minus omega t. Now E naught vector times exponential of I k dot r minus omega t is our actual electric field vector. So we can write it as JD vector equals to minus I omega times epsilon E vector. Now we'll take the ratio of the magnitude of the conduction current density vector, that is JC vector, and the displacement current density vector, that is JD vector. So it can be written as mod of JC vector divided by mod of JD vector equals to mod of sigma E vector divided by mod of minus I omega epsilon E vector. So we'll get effectively sigma by omega epsilon. Now as we are given the medium as semi-transparent medium, for that we have the condition that sigma by omega epsilon is very less than 1. This actually implies that the medium is the poor conductor or lossy dielectric. Now if we implement this condition in the expression of the ratio of JC vector and JD vector, then we will get mod of JC vector divided by mod of JD vector equals to sigma by omega epsilon which is very less than 1. So this implies that mod of JC vector is very less than mod of JD vector. So we can conclude conduction current for in this media is very less than displacement current, which is option B is given in the question. So according to our solution, a medium is semi-transparent to an electromagnetic wave when the answer is option B, that is conduction current is very less than displacement current.